This is January 2010, question 2 from paper 4, and this is again a description of Charles' law, which no longer is on the new specification, but Charles' law requires us to have a water bath. We then have a thermometer to measure the temperature. Okay, so we have our thermometer measuring the temperature. We have a stirrer, and we have a capillary tube which is open to the air with a little bead of sulfuric acid which traps a fixed mass of gas in here. So this is our fixed mass of gas in this area here. This is our water bath in here, so there's our thermometer. Sorry, one thing we need to put in then is our ruler so that we can measure the scale, or sorry, we can measure the length of the, right, so we've got a stirrer, and capillary tube, ruler, and then we're going to heat from below in order to get that. So what do we do here? So the water bath is heated and stirred continuously. So the water bath is heated and stirred continuously, and a series of temperature and length of series is measured. So all of those things, so we have the water bath heated and stirred continuously, and a series of temperature and length of air column is measured over a range of temperatures. And a graph of volume against temperature is plotted. Alright, we then come to a calculation where we have a container of volume 4.3 times 10 minus 2 holds 3.1 times 10 minus 2 kilograms of an ideal gas at a pressure of 0.4 times 10 to the 3, sorry, 0.43 times 10 to the 5 and a temperature of 17. Right, so we're going to use PV equals nRT, and we're looking for the number of gas molecules in the container. So we know that it holds, and we have 3.1 times 10 to the minus 2 kilograms of gas, and so the number of molecules, first of all we need to work out the number of moles, so we're going to say N is equal to PV over RT, so that's equal to 0.43 times 10 to the power of 5 times 4.3 times 10 to the minus 2 divided by 8.31 times 273 plus 17 is 290. Fill that all in, and that gives you 0.9 0.768 moles. And so the number of molecules then will be 0.768 times 6 times 10 to the 23, and that is equal to 4.62 times 10 to the 23 molecules. Okay, so we didn't need to have the mass at that stage, we just used PV equals nRT, work out n, the number of moles, and then multiply by the Avogadro constant. Calculate the root mean square speed of these molecules. Well, we're going to say a half mc squared brackets equals 3 over 2 kt, and m in this case is going to be equal to, well, it's equal to the 3.1 times 10 to the minus 2 kilograms divided by 4.62 times 10 to the 23 molecules, and that gives the mass of an individual molecule. And then we're going to say, if we take a look up above here, the half goes down, so we get c squared is equal to 3 kt over m. So that means that c squared's bracket is equal to 3 times 1.38 times 10 to the minus 23 times, and the temperature was 290, divided by, well, that becomes 3.1 times 10 to the minus 2 on the bottom, times then 4.62 times 10 to the 23 goes on the top line. So that's what c squared is equal to. So CRMS, this root mean square value, has to be the square root of all of that up above. And when you put 3 times 1.38 times 10 to the minus 23 times 290 times 4.62 times 203 divided by 3. Take the square root of all of that, that gives you a value of 423 meters per second.